All right, last few lectures we have been reviewing the classical control systems, and we saw many aspects of that including frequency response. So, some of these I mean these are the references for that if you want to study further details. The first one is my first choice, of course, I have taken many examples from there. So, that should be comfortable for you to read. The second one is also a good book, but it primarily I like this frequency response concepts as well as some concepts of modern control theory like state space systems and all that, actually state space representation. We will study that later. The third one is we will see lot of examples. It is a SCOMS outline series. So, if you really want to practice a lot of examples to get comfortable about yours, I mean the topics and all, you can see that. The fourth and fifth are primarily we will see lot of applications of this theory what we study here in flight control applications, aerospace control, especially to aircraft controls actually. And the last one is about engineering mathematics. So, some of the mathematical concepts, if you want further references, then you can probably see that actually. Before we move on, there are some points to remember. We have discussed that at length in the first class itself, but still to recapitulate. First thing first, the block diagrams are not circuit diagrams. That means, the things that we study here are not necessarily confined only to electrical engineering, they are very much confined to mechanical, aerospace and things like that. Circuit diagrams contain electrical circuits per se, but block diagrams is a diagram representation of ideas basically what we have and things like that. Okay. Then remember that stability and robustness are necessary for any good control design. We cannot get away from there, we have to talk about that. However, after that one must look at other performance conditions as well, that is like fast response, optimality, etc. Then also remember that invariably we do not select a high control gain, because there are good and bad things. Good thing is robust stability and good tracking behavior, however bad effects is control saturation and noise amplification. So, while you tune your gains, you should remember these things so that you can select some gain judiciously actually. Having said all that, also remember that intercoupling of variables, nonlinearities, control and state saturation limits, time delays, quantization errors, etc. Many practical aspects will always be there, and hence classical single input single output approach may not be adequate. That is why we are there in this course to study advanced control techniques actually. So, those are the necessary for doing that. I thought before we move on we should remember these things invariably. All right, that is what this end of this last class, and we will move on further to this particular lecture. We talk about some basic introduction of atmospheric flight mechanics. There is nothing to do with too much extensive detail. I mean this is a course by itself. We will talk about many details of that, but I assume that many people who study this course may not be knowing anything about flight mechanics. For them it becomes a small introduction of basic principle, how things fly actually. Then later on we will see some of the equations involved in that and how to manipulate that using control system theory. That connection will build on later, but this particular class will just see some basic principles of flight mechanics. First of all, there are various aircraft designs. If you see, first to fly probably goes to this particular gentleman here. His name is Otto Lilienthal, and he actually is the first person to make repeated successful short flights actually. So, you kind of mimicking the bird sort of thing, he attempted that actually, and essentially used a fixed wing glider, and then obviously died in a crash in 1896. And purposefully he knew that the risk involved, and he kept on saying that sacrifices must be made actually, and that is a great sacrifice in fact actually. So, he is the first person to attempt flying like a bird. Then obviously we all know that the next big credit goes to Wright brothers, okay, and they started as glider engineers and later on pilots as well, and they did lot of internal testing followed by optimization and things like that of the wing structure and things like that. However, the most credit for this Wright brothers successful flight goes to the control surface actually. That means they are the first persons to realize that uncontrolled flights are simply not possible. Okay, you need to have a control system for successful flight actually. So, that is the reason probably why they were successful where others were not that successful actually. It is also the first engine power flight in 1903, just about 100 years back, 100, 105, 106 years back actually. Okay, so, within that tremendous improvement in this field. remember just about 105 years back nobody knew how to fly basically, they are all surface transport only, but air transport was just not there actually. Now, after that you can skip a gap of about 30 years probably, and then we will go a little bit to the modern era. This is something which people started what is called as biplane. You can see that there are two wings here, one bottom, one top. Through that essentially creates additional lift to support your structure actually, okay, at the expense of a little bit additional weight also by the way, because the more structure you add to the system, the weight becomes more as well actually. It had high maneuverability, it was very popular in the early days of aviation actually. So, I mean sometimes people even use this for war applications in World War actually. Okay. Then there are other applications, there are other many designs has come up over the period of time. The next thing probably you can see is this is a very long wing, okay, essentially mimicking eagle flying. Okay. If you have eagle flying, I mean they just we can constantly do that. This is something called high aspect ratio, that means the wing span is very long. Okay. So, it has I mean it is a very efficient wing in that sense actually. Okay. However, it cannot fly at low altitude and things like that, it has to fly at a relatively high altitude and it has a low speed, it can also take low payload actually. Okay. So, these are like various consideration point of view, people will use many different things. This is I mean and this is just what I give here is just a small glimpse of things actually, largely collected from internet. Okay. So, this part of it. Then coming to commercial aircraft, this is the best possible aircraft available in market today. Okay. Commercial aircraft, the Airbus 380, okay. The strong competitor from that is Boeing Dreamliner, which is being designed, it is not yet in service, but this is in service. So, what are the aspects that you are looking for in commercial aircraft? You look for something like high lift versus drag ratio, that is invariably there in all aircrafts by the way, but the moment your lift to drag ratio becomes more and more, your efficiency of flying, efficiency of the aircraft design is higher actually. So, then in addition to that you also look for high fuel efficiency, high reliability and safety requirement. You carry so many passengers out here in a regular basis. So, you cannot compromise on safety issues, and also remember these are all long flights as well actually. So, you really require good handling quality, so that pilot can fly it in a good way, okay. Whatever he expects the aircraft responds that way, and then there is a strong requirement for passenger comfort as well. Okay. So, the too much of vibration, too much of oscillations are kind of not required out here actually. All weather operational capability is a requirement for airline operation, profit operations and all that. Okay. However, you remember the speed and agility or what is known as maneuverability are not that critical out here actually. Okay. You can nicely take off, go, land, and as long as you maintain safety requirements and passenger comfort, good handling quality and things like that, then you are very much okay. And on top of that you have to assure that the aircraft design is very efficient with good engine quality also, like fuel efficiency has to be very good here. Then coming to the next class, this is a fighter aircraft, there is a slightly role reversal out here. What you really require is high speed, high climbing rate, high maneuverability, stealthiness and things like that actually. Okay. So, here efficiency and is not that much important actually. If I require, I can pay a little bit extra money for my comeback to superiority actually. Okay. So, I have to overpower the enemy. So, for that I require all these actually. So, then these are typically characterized by very powerful engines, they are short wings, high chord length, complex geometry, large control surface, because you really require high maneuverability, that means high control actuation and things like that. High fuel consumption is also there, and hence it has some limited operating range as well. Remember, it cannot carry heavy amount of fuel either basically. Okay. So, all these limits is operational. So, there are concepts like for refueling the aircraft on the fly, that means as it flies it can be refueled as well actually from a oil tanker and things like that actually. Okay. So, there is a complete role reversal here compared to commercial aircraft to fighter aircraft. Commercial aircrafts are purposefully designed to be very stable and kind of robust application, safety requirement, things like that. Here it is purposely made unstable, and control design makes sure that the closed loop system becomes stable. The open loop is really unstable actually here. Okay. Then there are various other designs. This is something called flying wing aircraft. That means you can visualize the entire thing as a single wing, and these are all requirements from stealthy considerations actually. It has high stealth capabilities, so that is low visibility radar, fuel efficient, it is also fuel efficient due to low drag, because typically it flies at very high altitude. So, the air density is very low, dynamic pressure is low, drag is low actually. We will see that just a couple of slides later actually. And normally, I mean this is typically not very popular for commercial aircrafts, because there is no window arrangement here. People do not like to sit in a kind of a blind hole. So, I mean without looking outside, they cannot just want to, I mean they do not normally do not want to sit in a dark room sort of thing actually. Okay. So, that is not very popular among passengers actually. Now, coming to the conventional aircraft geometry, if you see the aircraft geometry, there are various parts of the aircraft that has specific requirements actually. It is a complex system of course. It has first of all engines which is required for propulsion. It has a huge fuselage sort of thing where people can sit, move around and things like that. That is where people sit. The wings here which largely are responsible for generating lift, and there are then there are like a cockpit here where passenger pilot sits, and there are a whole lot of instrumentation out here. Okay. And after that there are a lot of control surface arrangement actually. Okay. So, this is something called, this particular thing is called vertical stabilizer, this is horizontal stabilizer, the entire thing, and then within that there will be like cutouts here which can actually deflect left and right actually. Okay, that way. If you see this particular thing, it can deflect left and right, this particular thing it can deflect up and down and things like that actually. Okay. So, then there are other arrangements like what is called a spoiler, slot, and there are ailerons, there are like flaps out here and things like that. There is a huge number of control surface that goes on here essentially as part of the wing or vertical or horizontal stabilizers, and there will be cutouts which can actually move up and down or left and right actually. Okay. So, through that the control moments get generated, and how it is done we will see that actually here. Coming to a different class, there is a tailless aircraft. What you see here is a complete tail arrangement actually. There is a horizontal stabilizer, there is a vertical stabilizer out here, but in this one there is no such arrangement out here. There is no wing. See, if you go there is a clearly there is a big wing and there is a tail arrangement here. Both of the things are kind of coupled out here actually. Okay. They are put it together for various reasons, and one of that is these typical aircrafts are typically supersonic. So, the shock wave will get generated and all that should not hit the wing actually, it should go outside the wing. Okay. So, once the shock is generated here, it will something be like this actually, it will go outside the wing, it will not touch it actually. Okay. Anyway, so that is one reason of that. There are other reasons as well actually. Okay. What happens here is the pitch control and roll controls, that is typically done through the pitch control is done through elevator and roll control through ailerons, that are done together out here, what is called as elevons actually. If they are differentiated, if they are reflected in a symmetric way, they serve as ailerons. If they are deflected in an asymmetric way, that is one up and one down, then they serve as ailerons as well actually. So, that is the reason for what is called as aileron plus elevator, the elevator plus ailerons, that is elevons actually. Okay. So, there are variety of things. Another things that is people have attempted is something called canard configuration. That means, instead of a wing, I mean instead of a control surface at the back, they want a control surface in the front actually. That is something called canard structure. Okay. Again inspired by some fish design, and some like some fishes have this structure actually, how they control their movement and all that, and some birds also have this actually. So, what it essentially does, there is a horizontal stabilizer and elevators are kept in front, the advantage being better control characteristics. What happens here is, if you will see it later, that if you have a elevator in the back, that actually creates a downward force first, if you really want to go up. Okay. If you really want to go up, this needs to be, I mean you need to create a force downwards, so that this entire, there is a moment upwards, so the entire aircraft actually kind of rotates upwards, and then it generates a lot of lift out here. We will see that mechanism couple of slides down the line. However, that means there is a force that is created downwards first here to rotate the aircraft in a positive sense actually. Okay. So, that means then this entire body of the aircraft essentially first goes down and then goes up. That is the nature of what is called as this non-minimum phase systems actually. So, that is kind of avoided here, because if you really want to go up, you create a force up. So, that if you create a force up out here, then there is a moment also upward actually. So, then there is no movement of going down and then going up actually, it simply starts going up and up and up actually. Okay. So, that is that you eliminate this non minimum phase behavior characteristics actually. However, a drawback actually the flow out on the aircraft gets distorted actually, because see if anything happens at the tail, the actually airflow is from front to back actually. So, anything that you do here, the flow disturbance does not affect the body actually, the flow on the body, but here it is not so, it actually affects the flow on the body. That means, the aerodynamic modeling becomes difficult actually. Okay. So, that means your control characteristics will be good, but you will be working with a model that does not have good fidelity. That means, you again compromise on that aspect actually. Okay. So, that is there are various structures that are available. This is only a simple few glimpses out of that actually. Now, coming to how this how these objects fly in the air. So, let us see that basically there will be like force and moment balances actually. Okay, let us study what is force balance first. So, any flying object in a straight and level flight, let us say, okay, has to counteract these four forces get generated and they balance each other actually. First thing is there is a weight component which is vertical. So, there must be a force which is upward which should counteract that actually. Okay. So, there is a weight which is balanced by lift, but this lift generation mechanism also creates a drag. Okay. There is we will see that the reasons for creation of drag is a force to the back, and hence even if you want to go in a constant velocity, you have to constantly cancel out this force, this drag force. That means, you really need a force to the front actually. So, there are four forces essentially in a straight and level flight. One is weight which is balanced by lift, and then there is a drag which is balanced by thrust. So, we need to see how these forces are generated actually. Weight is obviously, it is very obvious. Okay, there is a mass and then there is a gravity. So, because of that mg force is acting downwards. So, that is kind of obvious actually. Let us see the other three. First thing is, how do you counteract that by lift? How do you overcome effect of weight by lift? So, lift is generated by differential pressure on upper and lower side of the wing actually. If you see the wing structures, there are variety of structures actually, if you see there, and once the aircraft starts flying front actually, that means you can visualize that the fluid flows backward. For this is one and the same things. Imagine a case where your aircraft moves through the fluid, or fluid moves through the body actually, aircraft. That is normally done in wind tunnel testing also. The aircraft is kept stationary, where the wind is flown over that actually. Essentially what matters is relative velocity actually. Okay. So, if you see that the flow, it starts from left and goes to the right probably, and then because of there are this flow field characteristics and all that, all details will be there in aerodynamics books and things like that. We will not go too much into detail. What happens here is, because of the way these wings are designed, and you see some sort of something called angle of attack, that means there is an angle between the velocity vector and the mean chord line. Okay. Because of that, the flow pattern is different, and hence what happens is there is a high pressure, okay, acting in the bottom, then there is a low pressure acting on the top actually. Okay. So, if you see that there is a differential pressure actually, okay, which builds on here, and if you integrate over the entire area, what happens is you get a force actually, net force upward. That is what is lift actually. And remember, if this angle is larger and larger, this is a smaller angle, 5° angle of attack, and this is actually very large angle, 40° angle of attack. What happens is you can get a higher lift, okay, and up to a limit of course. Okay. And after that again this lift fellow starts decreasing basically. Okay. So, essentially what happens is, if you increase this angle keeping your speed constant, then you can increase the lift actually, but the price to pay is your drag also becomes more and more high. Okay. So, that is the drawback actually. Okay. So, going to little bit on this aerofoil theory, what aerodynamic people call, there will be various ways. Suppose I take a wing and cut it through basically, okay, vertically, then I will see something like some sections like this, and these sections play a very good role in generating lift actually, and there are variety of ways of designing that, and different applications actually. So, that means the bottom line is, there is no ideal aerofoil actually, airfoil. Okay, depending on what application you are talking about, we will probably select a airfoil that is best suitable for that application actually. Okay. So, choice of the airfoil depends on flying speed, wing loading, construction method, what technology you have, and kind of flight, what kind of flights you are talking about, placement of the I mean placement on the airplane, where you want to place the wing, things like that actually. Okay. But there are variety of studies including Wright brothers themselves studies a lot of things, but after that there is a lot of studies about that, and a variety of wings are available now actually. Yeah. Now, coming to the mathematics part of it, what is beauty for people like us in control system is this lift expression. If you see, this is universally same. This is something given like this actually. This q bar is something called dynamic pressure. Okay, is given by half rho v square. S is something called weighted surface area of the wing. Okay. These are typically surface area is given to a particular, it is a number actually given to us from aerodynamic people for a particular aircraft configuration. Then rho is obviously atmosphere density and it is a function of height actually. We will see that how it varies, and then there is a v square which is relative velocity of the air actually, okay, with respect to the vehicle. So, this term is dynamic pressure. Okay. This is surface area and this is CL which is lift coefficient. Now, no matter whatever aircraft you talk about, whatever design of the aircraft, whatever speed regime you talk about, let us say supersonic, subsonic, whatever flow pattern, anything any flying object, the good thing is the lift expression does not change actually, expression is given like this, where all other effects are embedded into CL. Okay. That means, the model that will be given to us typically will contain some expressions on CL depending on the application that we talk about, and that may be like given in as a table of data and things like that, as a function of Mach number, as a function of angle of attack, things like that, and that can change, but the overall formula will not change actually, and that helps us quite a lot in control design and all that. Now, coming to the dynamic pressure part of it, what we saw here is half rho v square dynamic pressure. And this dynamic pressure is actually, you can visualize the total pressure of any fluid is partly from static pressure and partly from dynamic pressure. The static pressure is rho g h, okay, that kinetic, I mean this potential energy sort of thing, and then there is a dynamic pressure which is essentially kinetic energy content actually. Okay. So, this is what plays a role in generating lift and drag essentially. Okay. So, the atmosphere density, if you visualize, I mean you see the universally this remains true by the way. So, if you see this at the distribution of air molecules, so on surface of earth is they are very dense, as you go up and up and up and up they are very sparse actually, and that is probably because of gravitational effect. Your surface of the earth, the gravity is very high, so you see lot of air molecules concentrated on surface of earth actually here. Once it goes up and up and up, they are getting more and more sparse actually. So, essentially what happens, the air density decreases exponentially, right. So, if you can visualize this plot something like increasing values being like this, and the altitude becomes more and more, okay, your air density starts decreasing actually. Yeah. What you see here is altitude. So, if you go up and up and up and up, your density of the air becomes low and low and low, and that decrease actually happens in an exponential way. Your atmosphere density is roughly given by this formula with a negative exponential actually. Okay. So, what happens here is the more height you climb, the dynamic pressure becomes very low actually, I mean lower and lower, ultimately it becomes very low and you will not be able to support your weight. Okay. So, that is why there will be altitude ceilings for any given atmospheric flying objects and all that actually. Okay. Anyway, so angle of attack formal definition, as I told, there is a free stream velocity and there is a mean chord line. If you see take that angle, then that is, so that is an angle which is called angle of attack actually. Okay. And that plays a very critical role in flow pattern distribution, as we saw that here. Okay, that is angle of attack, the flow pattern entirely depends on that quite heavily, and that angle plays a very important role in CL essentially. Okay. CL, what we see as CL here, okay, that will be typically a function of alpha actually. Okay. And then this is this 1/4 of the chord line is something called center of pressure actually, that this is where if you take incremental pressure or incremental force and then sum it up, then the moment becomes 0 out here actually. Okay. So, that means the entire lift and drag gets generated out here. Okay. This is called center of pressure basically. Okay. Right. Now, coming to the gross behavior of CL versus angle of attack, this is what happens. It starts like fairly like a straight line, but at high region it goes and stabilizes and then it decreases actually. This is something called stall angle of attack, roughly of the order of 17, 18, 20 degrees depending on airfoil actually, what airfoil you are talking about. Also remember that when angle of attack is 0, you still have a positive lift actually. Okay. Only when the angle of attack is some negative value, okay, then only you will have something like lift 0 out here. Okay. So, any for 0 angle of attack you still have some lift generation actually. Now, coming to the drag part of it, the drag is also given by very close formula. Instead of CL, what you replace is CD. Okay. But also remember that CD is roughly a function of like this, a function of CL in a quadratic way. So, CD is essentially CD 0 plus KCL square, that means it actually varies in a quadratic manner basically. Okay. So, any amount of lift that you generate, this additional term keeps on building actually. Okay. And also remember, even if you do not generate any lift, even if CL is 0, still CD will be there. Okay. So, drag will be invariably there actually. Now, there is another variety of notions that are available, I mean that are required in flight dynamics understanding and all. One of that is called as Mach number, and this is a non-dimensional quantity. This is essentially defined as velocity of the object relative to the medium, whatever your flying object velocity, divided by sonic velocity. That means, this velocity of sound in the medium at that particular condition actually. Okay. So, velocity of sound is also a function of height, remember that velocity, I mean it does not remain constant. But if you talk about 25 degrees centigrade and things like that, the formula is given like this, okay, and it is largely a function of air temperature essentially. And also remember, temperature of air also varies along with height actually. That variation I have not given here. It does not vary exponentially decaying manner, but it does vary with height as well actually. So, it remains like at sea level at 25 degrees centigrade room temperature, things like that, you can take this value as 340 meter per second actually. Now, what is the beauty of that is this particular number plays a heavy role in defining what is called a subsonic speed or sonic speed or transonic, supersonic, hypersonic, things like that, because the aerodynamic behavior is a strong function of this Mach number actually. Okay. So, as long as you have the subsonic speed, there will not be any shock wave generation. Okay. Your aircraft velocity is lesser than speed of sound. Whereas any supersonic thing and hypersonic thing, they will create shock waves as well actually. Okay. And unfortunately, it turns out that during this transonic region, the aerodynamic phenomenon is never understood very well even now, and hence the modeling becomes very inaccurate actually. Okay. So, these are some of the reasons why this Mach number plays a heavy amount of a role, and also remember CL and CD are typically functions of Mach number as well actually. Okay. Now, CD how it varies with Mach number is something like this. In a subsonic region, there is a fairly constant value. Okay. Essentially, what we are talking is this that CD 0 portion actually, not KCL square term. Okay. Then it starts building up very fast. Okay. Then it will again decrease and it will stabilize after some time, after high speed actually. Okay. Like about Mach number 1.52. There onwards this fellow will not change actually. Also remember that this number where it stabilizes is higher than this number. That means, if you really want to fly a supersonic speed, then your drag is going to be very high compared to subsonic thing. That is why these commercial aircrafts are very successful in subsonic region. The moment you go to supersonic, the efficiency goes down. That is why this Concorde aircraft was very expensive to fly actually. Okay, that was supersonic aircraft. It was very unsuccessful commercially basically. Okay. Now, coming to drag components, you can visualize why this drag is coming. There are something like skin friction drag, pressure drag, induced drag, various other components as well. Okay. Let us see very quickly. Skin friction drag is essentially because of surface area non-smoothness actually. So, if you take a very big microscope, you can see what you feel like smooth surface is not really very smooth. It has some I mean surface roughness. Because of that, there will be local circulations and things like that. Essentially a friction sort of behavior actually. Okay. That is called skin friction drag. Now, form pressure drag or something, it depends on the form of the object. Okay. Suppose you take this vertical plate sort of thing, that will where your drag will be maximum, okay, because the entire flow pattern is completely disturbed actually after that. Then if you take a perfectly spherical object sort of thing, things are slightly better. Okay. Then if you take this particular shape, then they still better, and if you can optimize this particular design, then it can be very very good compared to all other things actually. Okay. So, that because of that reason you see this new generation cars, the expensive cars what comes with that, they also go for some sort of aerodynamic design, because once you see the speed of the car is higher and higher, you essentially laid up with this pressure drag actually. So, to minimize that, you see this, there is a typical shape of these cars will be somewhat like this actually, somewhat last two sort of thing, new cars actually what comes there. Now, induced drag is essentially we discussed about that as and this is primarily because of this flow pattern distortion, because of this vortices that gets created afterwards actually. As the angle of attack is more, this flow pattern gets the vortice generation is more. So, you get induced drag more and more, and so this is also a function of flow separation over the entire body that happens more while maneuvering actually. So, if you are flying straight and level, then the aircraft structure is designed to be optimal in that mode actually. Any time that takes a turn, the entire flow field is distorted. So, you will have more and more vortice generation and things like that. So, your induced drag will be more and more actually. Okay. So, it is a strong function of your what is called as lateral acceleration actually. So, the moment you generate a lateral acceleration or normal acceleration either way, then it will have induced drag component will go more actually. So, one of our control design methods we will see later in if covered, we will see later that this missile guidance application particularly, I do not know whether I will cover that in one of our lectures or not, but one of the reasons one of the objectives there is to minimize the induced drag through an optimal way of latex generation actually. That is one of the conditions that we lead to, and essentially this what is called as PN guidance, which is very popular in missile guidance, that implicitly does that anyway. Okay, so those things are there actually. Now, coming to the thrust force, see remember there are we talked about weight versus lift, and drag versus thrust actually. So, this thrust generation happens through a variety of ways, and you have to essentially use an engine to do that. And it can happen through a propeller, through a turboprop, turbofan, turbojet, ramjet, scramjet, and a variety of things. It is a field by itself, and we are not going to discuss too much on that. What we really need is a thrust generation mechanism in control system design, as well as to a limited extent this thrust generation mechanism will also give us some sort of control force actually. We can manipulate the thrust required, the magnitude as well as the direction to a limited extent. This is a thrust vectoring what we call in fighter aircrafts. Okay. So, these two are possible available, however, variety of ways of generating thrust actually. Let us very quickly see that. So, jet engines can be classified into like turbojet, turboprop, turbofans, things like that, and this is roughly the behavior what you expect actually. Okay. I do not know whether this slide is not very clear. So, what is plotted out here is Mach number versus specific impulse ISP. Okay. And this ISP, okay, this is by definition something like thrust by mass flow rate actually. Okay. Okay. So, how much mass flow is there, how much fuel you spend essentially to generate that much amount of thrust actually, that kind of a idea there. So, if your ISP is higher and higher, your engine is operating in a very good efficient manner actually. But unfortunately, what happens is if you really want to fly with Mach number higher and higher, okay, that is no more possible actually. So, if you see this class of vehicles actually what will operate on turbofan sort of idea, okay, they operate on very low speed actually, Mach number less than 1. So, your efficient ISP can be kind of high actually there, okay, this region actually what is all. On the other hand, this is what is rocket engines. Rocket engines are very inefficient, their ISP is very low. However, you can fly with whatever Mach number you want, Mach number 9, 10, whatever you want actually, you can go through whatever degree of speed you want actually that way. There will be something in between, there are some concepts of something called ramjet, scramjet, things like that. This is because of something called ramming effect, that is the name ramjet comes, then the supersonic combustion ramjet, that is scramjet and things like that actually. So, they are essentially varied, this modern aircrafts essentially work on either turbofan or turbofan with afterburners, big things actually, or sometimes they work with turboprop as well, okay. And some applications we will see actually. The propeller design, propeller engines are essentially old ideas, and they are one example is this aircraft which was used by England in Second World War actually, okay. So it was in practice actually, it was operational, successful. Turboprop engines, you see even now there are many ATR flights that we take, short duration flights with lesser number of passengers and all, they are efficient in that region. They are essentially operate in that region actually, like okay, this turboprop variety sort of thing actually, okay. So ATR flights do use turboprops actually. This is, I think many of you have seen this in airports, and probably many of you have flown also actually here. Turbofan engines are typically used in big commercial aircrafts, okay. And turbofan engines, remember, are very less noisy actually, because the entire rotational mechanism, if you see, they also go inside the casing basically, okay. So that they are both efficient as well as they are less noisy actually, okay. So that is where you see these are used in commercial aircrafts for big aircrafts basically, okay. For example, A380 uses that actually. Turbofan with afterburner essentially, remember, if you see, go back to this flow chart, turbofan with afterburner is this region actually, whereas only with turbofan is that region, okay. So if you really use afterburner, you can push that velocity to Mach number to supersonic region actually, okay. So your ISP will be lower, that means your engine efficiency will come down, but your vehicle speed will be higher actually, okay. That is where your fighter aircraft, for example, LCA will uses that actually, okay. This is a light combat aircraft being designed by YADA actually, primarily. Ramjet engines are used in, essentially they are used in missiles, because Ramjet engine operates somewhere here or very low specific impulse basically. So the attempts are being made to make it commercially successful as well, but because of this they are typically a concern actually, okay. So they are supersonic, I mean this is something called ramming effect basically. When your vehicle velocity is more than Mach number 1, you are in supersonic region, you really do not need too much of this complex mechanism what you see here. There will be like compressor is not needed, turbine is not needed, like that actually, okay. So and then but the shock wave management becomes a critical issue there actually. So your shock wave management, inside shock wave goes inside the engine, and you really do not I mean have that much liberty here to manipulate as you want actually. So there are critical technologies out here actually, okay. And then still further technology boundaries towards that, I mean this is not successful yet. However, people have only test flown and demonstrated for short durations that you can even go up to Mach number 9 actually, okay. That has been demonstrated by NASA in that X-43 flight actually. This is a missile operating this real missile operated I mean developed jointly by India and Russia. It has been test flown and being inducted actually. So this is, so variety of missiles are available which will really operate on Ramjet principle actually. This is just one of that actually. Now coming, these are all so called like force balance we studied. Now let us see very quickly what is moment balance as well. That is, moment is also critical in a flying object, and essentially moment is the one which gives us controlling capability of a vehicle, not force actually. Force gives us propulsion characteristics and all that, but by changing the moment, changing the rotational behavior, we will be able to control the vehicle actually, okay. That is where we see that. Now for just a quick review, what we saw there force balance is weight, lift, drag and thrust. Also remember that there will be a side force component actually, that we typically neglected that, assuming that to be 0 there. So this drag is not perfectly, see thrust is normally aligned perfectly like to the nose sort of thing, that is by design. But drag you do not have a choice typically. Drag is actually opposing to the velocity vector, and velocity vector all the time need not be aligned to the vehicle nose actually. That can go somewhere inclined, and once it happens that way, okay, that is the velocity vector sort of thing, let us say, okay. The velocity vector is somewhere something like this. This is velocity. Then there will be opposing force which is there, and that you can resolve into two components. One will come that what we have seen as drag before, okay, and then there will be a side force which will also come there. Typically there is no mechanism to cancel the side force actually. So in general we do not want side force generation, okay. That is what is called as like turn coordination actually, coordinated turn and all that actually, we will see that. Anyway, so the basic moment balance is essentially three moments are there. One is rolling moment, another is pitching, and another is yawing. Okay, essentially this is something called body axis actually. You can visualize an axis frame sitting on the center of gravity of the vehicle, where x axis is pointing to the nose, y axis is to the what is called as starboard or the right side of the wing, and then there is the vertically down is something called z axis actually. So, any rotation if you can grab that axis that way, okay, pointing to the right or whatever, this is this side is your like thumb should point out, then your other fingers will point in that direction actually. Okay, sorry. Okay, if your thumb is in the direction, this will become in that direction actually. So, okay, this is the positive rolling moment. Okay. Similarly, if you grab this axis, your thumb pointing towards that, then the other fingers wherever they point, that is called pitching action actually. Okay. We will see that one by one here, but you will see that first is roll. Rolling is about positive x axis, pitch is about positive y axis, and yaw is about positive z axis actually. Okay. So, roll, pitch and yaw, those are very critical in control system design applications as well. I mean, we will see that actually. So, what is how do you create a rolling motion? Suppose you really want to cancel the unwanted roll, or you want to create a wanted rolling thing. Okay, you want to take a turn, then you have to create a roll as well. Okay, rolling and yawing are typically coupled actually. If you see this roll and yaw are typically strongly coupled, whereas pitch will be slightly decoupled from these two normally. Okay. In general, all three are coupled, but these two are strongly coupled. Even in a linear setup, we cannot neglect the decoupling part of it, whereas this part is fairly decoupled from these two actually. Okay. Now, how you create a rolling motion is essentially done through creation of differential force through these cutouts actually, what are called as ailerons actually. So, there is a cutout here, okay, in the right side of the wing, and there is a cutout here in the left side of the wing. Suppose your left side you turn it down, then your angle of attack essentially goes a little bit higher in this side. So, that means your lift CL becomes more. So, you get a larger lift force here, whereas you get you deflect in the other side, you get a lesser lift force out here, okay, because angle of attack, the effective angle of attack you are reducing by deflecting it up actually. By deflecting it down, you are increasing the angle of attack. So, the lift force becomes more. So, what is happening? You have a larger force here and a smaller force here. So, that means there is a differential force which is not on CG, it is far away from CG. So, it will create some sort of a moment here actually about CG. Okay. So, that effect let us see. So, the moment you deflect like up and down, okay, that will roll like that actually, this aircraft. Okay. This effect is called rolling effect. Similarly, if you see the pitching movements, how do you create a pitching action is largely through this elevators. So, they are reflected symmetrically actually, either both up or both down. Once they are both up, then you have essentially there is a downward force, because these are differential downward force, remember that, it need not be the complete downward force, aircraft need not go down. Okay, but there is a slight downward force here, but it is far away from CG, remember this length is very high. So, you get a large moment which gets generated out here actually. Okay. So, then that will create some sort of a upward movement actually, the pitching action basically, that is what will happen while deflecting the elevators. Okay. And similarly, happens the yawing motion is typically controlled by rudder. Okay. Rudder, if you generate left or right, so there will be a side force generation essentially. So, that side force will create a resulting motion actually in a yawing sense. By the way, this rudder is also used to nullify this side force that I talked actually. If you really want to nullify this side force, then the rudder is the mechanism to do that, but it is not very effective that way. It is very effective in generating a moment because of the moment arm, but generation of force is not very much capable. None of these control surfaces are very capable of generating heavy amount of force. They generate a small amount of force, but because the moment arm is long, the moment creation becomes strong actually. Okay. So, this is what happens through rudder movements actually. Okay. Now, coming to that this motions what you see neatly, these are actually coupled motions. Okay. These are not decoupled motion. Let us see that one at a time again. Okay. You have these three axes x, y and z. Any moment, this moment or rolling action about this is called rolling actually. Okay. angular motion about this x axis are called rolling action. Then angular angular movement along y axis is called pitching action, okay, and angular movement along z axis is called yawing action. Okay. And for controlling the roll, we have ailerons here. Okay. Okay. For controlling the pitch, you have elevators right there. Okay. For controlling the yawing, you have rudders, which is right here. Okay. Now, there are additional things, as you know, these are flaps and these are spoilers and these are slats and all that. They are typically used during takeoff and landing essentially. All other time they will not be used. So, they are momentarily used to either to for example, if you spoiler, you cannot make it down, it is on the surface of the wing, top surface of the wing. So, you can only take it up. Okay. But that is, once you do that, what happens is there is a heavy amount of drag created actually. Okay. And these are done not differentially, they are done symmetrically. Okay. You cannot do it differentially anyway. Differentially you can do, provided you deflect this one 2 degree and that one 5 degree, I mean that is a different issue actually. But typically both have to go up actually, one cannot go down and one cannot go up actually that way. So, once you take both up and with equal angle, then what happens, this moment that you generate is counteracted by that moment. So, essentially the moment generation will not be there, but what will happen is there will be a force generation, that is additional drag will create actually. Okay. That is typically used while landing the aircraft. Once those of you who have flown the aircraft and seen landing carefully outside the wing, you will see that during landing, after touchdown, suddenly these guys go up to create heavy amount of drag. It is essentially like a braking mechanism actually. Okay, used to do that. The slots what you see there, they are deflected downwards typically to have more flow attachment, so that your lift becomes more. Okay. So, that happens during essentially takeoff and landing actually. The lift becomes more, drag also becomes more, I mean that way, either way, whatever you want actually. Okay. While taking off you want lift more, while climbing down, while touching you want drag more actually. Okay. So, that way they are used actually. Flaps are also deflected vertically down that way. So, there are, I mean these are primary control surfaces, there are many other secondary control surfaces as well. We are not going to talk too much on that. For example, this elevator cutout what you see here, what you saw here, there will be a further cutout somewhere here, which is something called trim tab actually. So, if you really want to fly on a trimming condition, then not only this has to go down, but that little portion at the end of that particular surface will go up actually. Okay. So, these are a variety of considerations you will see in a flight mechanics course, this is not a flight mechanics course, we will not talk so much detail about that, but many other considerations do come into picture, and there are all sort of forces and moments that you see, they are all coupled actually. Okay. That means, whatever forces you see here they are not separated from each other at all actually. Okay. So, that is how it is a nonlinear coupled equation. And there are 3 axes, you remember that on the 3 axes you will get 3 forces and 3 moments, and all of these forces and moments are governed by Newton's second law actually, and each Newton's second law is F equal to mx double dot, remember that. So, once you have double dot formulation, essentially you can convert that into state space form in single dots in 2 differential equations. So, what essentially you have is 12 differential equations, so 3 axes, 3 forces and 3 moments, 6 actually, 6 each are second order equations. That means, you will get 6 into 2, 12 equations in total actually. So, those 12 equations will be coupled with each other, and that are the equation, I mean that set of equations are the one that we are going to use in nonlinear control design for flying objects in general and aircrafts in particular actually. Okay. We will see those details little later actually. And there are variety of other things. So, suppose you really do not care about so much of details, then something called point mass equations are available. You care about, let us say, missile guidance over a long duration. You really do not need to care as far as trajectory optimization or as far as guidance problem is concerned. You really do not care too much about how my aircraft or how my missile is kind of what is the attitude of my missile, what angle it makes actually. Okay. As long as I go close to the target, I am okay. So, as far as guidance problems are concerned, they are typically you will use point mass equations, not so much detail actually. But when you come to control design in a good way, you really have to use what is called a 6-DOF equation. That is what I just talked about. 3 axes are there and 3 forces and 3 moments, and each are of second order equation. Okay. That essentially consists of what constitutes a 6 degree of freedom equation of motion actually. And that is what will be used for control design in general actually. Alright, so all these things we just saw that one more time. Let us say this is aileron for rolling control, that is what will happen. Okay. These are, remember, these are getting reflected, the dark ones, the solid ones actually, that is ailerons, and this is elevator. So, these are the ones which are used. Okay. That is how it will be used, then let that, and this is a rudder thing which will deflect, if you deflect left and right, that is what will happen. This is called yawing motion actually. Okay. Now, coming to the sensors, also remember that when you talk about automatic control of aircrafts, you really require a heavy amount of sensors to what goes on in the vehicle actually, and it is a very sensor rich system rather the modern day aircrafts or missiles, whatever we talk about, launch vehicle, missile, say even satellites, all these are very highly sensor rich actually. And in the sense you can get the same information using multiple sensors as well. That gives us sensor redundancy, that one fails the other is still there. It also gives us data fusion capability. That means, if you take one measurement through one sensor and the same measurement using 3 or 4 sensors, I can fuse it in a good way to get a very good accurate information actually. So, all these are used actually. Now, what are the typical sensors that goes in an aircraft? You can think of first as an altimeter. You really need to know what height you are flying. Okay. Then there is a air data system which gives a host of information like airspeed, angle of attack, Mach number, air temperature, etc., etc. Many things will come from there. Then there is a magnetometer sometimes used for heading things. Remember, if you put a compass sort of things, okay, it will always point to the north actually. Okay. So, if you put a very good compass, let us say on CG or something, it will always point to the north. So, you will know which heading you are going actually, what is the direction of your vehicle, that is a magnetometer. And all these have their own limitations and advantages actually. So, depending on what application you talk about, you should use the sensor information in a clever way rather. Okay. And what is invariably there in modern day flight of the flying vehicles is something called INS system, inertial navigation system, and essentially that consists of accelerometers and gyroscopes. These are invariably there. Okay. Accelerometers are essentially, they measure translational motion of the aircraft in 3 axes. They will motion this translational speed, translational acceleration, things like that, they will measure that. That means, along XYZ axis, what we saw here, okay, along XYZ there will be a velocity component, right, those are called UVW and things like that, those quantities will be measured through accelerometers. And then the rolling moment, the angular motions and all, they will be measured by this gyroscopes. Okay. So, rotational motion of the aircraft in 3 axes are measured by gyroscopes typically. Then there is another set of sensors which is called GPS, global positioning system. They essentially operate through satellite information and all that. There are 24 satellites there up, and then you acquire some 4 good satellites at any point of time around the globe, that is available by the way. And then out of that you collect the information of the satellites and from at which point of time they emitted that signal, and using those information you calculate your own position actually in a very good way. It turns out to be a highly accurate system. However, it is subjected to signal availability from the satellites, and essentially that is controlled by US. So, there are also like parallel systems available like GPS, what are called GLONASS, then called something are still getting developed like Gaggan and things like that actually. Okay. They are same concepts. They operate on 2 frequency band also, one is available throughout the world, that is the civilian frequency band, and there is also a military operation band which they normally do not give it to other countries unless it is a very highly friendly country. Probably it is available only to Israel other than US, maybe other countries is not available actually. But it is a highly accurate system. It not only it measures position, it can also measure ground speed as well and things like that. This is not an exhaustive list, there are other sensors available as well actually, something for example star sensors, they are available for altitude measurement. But they can be used exo-atmospheric, that means for satellite application they can be used actually. So, that itself is a technology by its in a huge way basically. And gyroscopes, they can call mechanical gyroscope, there are fiber optic gyroscope, there are laser gyroscope, there are many things actually like that. Accelerometers similar way, there are for UAV applications, they are typically MEMS level micro electromechanical system, they are manufactured that way actually. They are low cost, but not that accurate systems actually. Okay. So, what I mean is a lot of information will keep coming through a variety of sensors which will be essentially processed by your onboard computer and to give a control command essentially. Okay. So, that is ultimately executed through actuators. Actuators will be situated now modern day aircrafts, actuators are situated right there where you really need that, and the command as everything goes through all sort of computation through flight computer, and essentially the signal is transmitted through a wire to this actuator system, which actually actuates the system. It deflects that aileron for example. Okay. So, what is the required amount of computation, that how much degree how much deflection you need to give, that essentially you compute using your flight dynamics, using your control system technology, everything. Now, ultimately you give a command to this actuator, that actuator takes the command electronically through wire and then executes it through some sort of like a motor and all that actually. Either it is a hydraulic system or it is a electrical system as well actually. Okay. This is because all these things happens through wire, not through extensive mechanical mechanism. These are also called fly by wire control system. Okay. Everything information is taken through a variety of sensors. They are processed through either through low pass filter or Gunnell filtering, whatever you want to do. Then those process information are used in flight control computer, control design algorithms. Ultimately, this the output of the algorithm is passed back to this actuator and essentially that is executed there. So, in a nutshell, putting it all together, there is a flight aircraft sensors which will sense the measurements, and then the pilot command also, pilot will see outside and all that. That also you can see that a huge amount of sensors that goes through pilot organs basically, like eye, ear, talk, all sort of things. Then he gives a command essentially that also comes to the control computer. It goes through a variety of computation, then it gives a control command which is essentially executed there. Okay. So, the entire control mechanism essentially deals with this flight control computer. What will deal here? We will talk about algorithm development essentially, using the various variety of models like point mass or 6 top or whatever. How do we generate a good control algorithm which will essentially be given to the controller actuator essentially. So, that is our entire objective here in this particular course actually. This is where I will stop for this class. Thanks a lot.